हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज फाइनली वो घड़ी आ ही गई है जब आपका क्लास 12th का भी लास्ट चैप्टर ऑडियो बुक में रिकॉर्ड कर रही हूँ। दैट इज द यूनिट 11 एल्कोहल्स, फिनॉल्स एंड ईथर्स। आप सबकी रिक्वेस्ट को देखते हुए धीरे धीरे करते करते फाइनली सारी ऑडियो बुक क्लास 11th एंड 12th केमिस्ट्री भी रिकॉर्ड हो गई। अदरवाइज मुझे लग रहा था कि बायोलॉजी रिकॉर्ड करना तो ईजी है, बट केमिस्ट्री को रिकॉर्ड करना काफ़ी डिफिकल्ट मुझे लग रहा था। बट जैसे जैसे मैंने देखा कि आप लोगों को वाकई में हेल्प करती हैं ऑडियो बुक रिवीजन में, सो उससे मुझे बहुत मोटिवेशन मिला और मैंने आप लोगों के लिए फाइनली ये सारी रिकॉर्ड कर दी। तो 11th तो हमारा कंप्लीट हो चुका है। 11th की पार्ट 2 की बुक मैं कंपाइल करके सारे वीडियोस एक साथ अपलोड कर दूंगी, बट क्लास 12th का एक चैप्टर बच रहा था, ये यूनिट 11, तो ये आज मैं कंप्लीट कर दूंगी। इसके बाद क्लास 12th का भी पार्ट 2 मैं जल्दी ही पूरा कंपाइल करके एक साथ अपलोड कर दूंगी। एंड आई होप कि आप लोग अपनी तैयारी को बहुत अच्छे से कर रहे होंगे, रिवीजन बहुत अच्छे से कर रहे होंगे और अपने दोस्तों के साथ में भी इसे ज़रूर शेयर कर रहे होंगे। और अगर आपको ये वीडियोस मेरी हेल्प करते हैं तो प्लीज़ इसको लाइक ज़रूर करिएगा। एंड अगर आप मेरे चैनल पर नए हो तो सब्सक्राइब कीजिएगा। चलिए टाइम वेस्ट नहीं करते हैं और शुरू करते हैं। यूनिट 11 अल्कोहल्स, फिनॉल्स एंड ईथर्स। थोड़ा सा मुझे कोल्ड है, इस वजह से आवाज़ में थोड़ा सा डिफरेंस आपको हो सकता लगे, बट आपके रिवीजन के लिए ये हेल्पफुल होगा। Alcohols, phenols and ethers are the basic compounds for the formation of detergents, antiseptics and fragrances respectively. You have learned that substitution of one or more hydrogen atoms from a hydrocarbon by another atom or a group of atoms result in the formation of an entirely new compound having altogether different properties and applications. Alcohols and phenols are formed when a hydrogen atom in a hydrocarbon, aliphatic and aromatic respectively, is replaced by OH group. These classes of compounds find wide application in industry as well as in day-to-day life. For instance, have you ever noticed that ordinary spirit used for polishing wooden furniture is chiefly a compound containing hydroxyl group ethanol? The sugar we eat, the cotton used for fabric, the paper we use for writing are all made up of compounds containing OH group. Just think of life without paper, no notebook, books, newspapers, currency notes, checks, certificates, etc. The magazines carrying beautiful photographs and interesting stories would disappear from our life. It would have been really a different world. An alcohol contains one or more hydroxyl groups directly attached to carbon atoms of an aliphatic system, while a phenol contains OH group directly attached to carbon atom of an aromatic system, that is C6H5OH. The substitution of a hydrogen atom in a hydrocarbon by an alkoxy or aryloxy group yields another class of compounds known as ethers. For example, CH3OCH3 dimethyl ether. You may also visualize ethers as compound formed by substituting the hydrogen atom or hydroxyl group of an alcohol or phenol by an alkyl or aryl group. In this unit, we shall discuss the chemistry of three classes of compounds, namely alcohol, phenols, and ethers. 11.1 Classification. The classification of compounds make their study systematics and hence simpler. Therefore, let us first learn how are alcohols, phenols, and ethers classified. 11.1.1 Alcohols, mono, di, tri, or polyhydric alcohols. Alcohols and phenols may be classified as mono, di, tri, or polyhydric compounds depending on whether they contain 1, 2, 3, or many hydroxyl groups respectively in their structures as given below. Here you can see monohydric, dihydric, and trihydric. Monohydric alcohols may be further classified according to the hybridization of the carbon atom to which the hydroxyl group is attached. Number 1. Compounds containing CsP3OH bond. In this case, a class of alcohols, the OH group is attached to an sp3 hybridized carbon atom of an alkyl group. They are further classified as follows: primary, secondary, and tertiary alcohols. In these three types of alcohols, the OH group is attached to primary, secondary, and tertiary carbon atom respectively as depicted below. You can see here primary, secondary, and tertiary. Allylic alcohols. In these alcohols, the OH group is attached to a sp3 hybridized carbon adjacent to the carbon-carbon double bond, that is to an allylic carbon, for example, primary, secondary, and tertiary. Benzylic alcohols. In these alcohols, the OH group is attached to a sp3 hybridized carbon atom next to an aromatic ring. For example, primary, secondary, tertiary, you can see the structures. Allylic and benzylic alcohols may be primary, secondary, or tertiary. Second, compounds containing CsP2OH bond. These alcohols contain OH group bonded to a carbon-carbon double bond, that is to a vinylic carbon or to an aryl carbon. These alcohols are also known as vinylic alcohols. Vinylic alcohol, CH2 double bond CHOH. 11.1.2 phenols, mono, di and trihydric phenols. Here you can see all the structure: monohydric, dihydric, trihydric. 11.1.3 Ethers. Ethers are classified as simple or symmetrical. If the alkyl or aryl group attached to the oxygen atom or the same are mixed or unsymmetrical if the two groups are different. Diethyl ether C2H5O C2H5 is a symmetrical ether, whereas C2H5O CH3 and C2H5O C6H5 are unsymmetrical ethers. 11.2 Nomenclature. A. Alcohols. The common name of an alcohol is derived from its common name of alkyl group and adding the word alcohol to it. For example, CH3OH is methyl alcohol. According to IUPAC system, Unit 12, Class 11, the name of an alcohol is derived from the name of the alkane from which the alcohol is derived by substituting E of alkane with the suffix -ol. The position of substituents are indicated by numerals. For this, the longest carbon chain, that is a parent chain, is numbered starting at the end nearest to the hydroxyl group. The positions of the OH group and other substituents are indicated by using the number of carbon atoms to which these are attached. For naming polyhydric alcohols, the E of alkane is retained and the ending -ol is added. The number of OH group is indicated by adding the multiplicative prefix di, tri, etc. before all. The positions of OH group are indicated by appropriate locants. Example, HO CH2CH2OH is named as ethane 1,2-diol. Table 11.1 gives common and IUPAC names of few alcohols are examples. Here you can see the common and IUPAC names of some alcohols. Cyclic alcohols are named using the prefix cyclo and considering the OH group attached to C1. See here cyclohexanol and 2-methyl-cyclopentanol. B. Phenols. The simplest hydroxy derivative of benzene is phenol. It is its common name and also an accepted IUPAC name. As the structure of phenol involves a benzene ring, in its substituted compounds, the terms ortho 1,2 disubstituted, meta 1,3 disubstituted and para 1,4 disubstituted are often used in the common names. Common name IUPAC name. You can see here phenol, orthocresol 2-methylphenol it is, metacresol, that is 3-methylphenol, and paracresol is 4-methylphenol. Dihydroxy derivatives of benzene are known as 1,2, 1,3 and 1,4 benzene diol. Common IUPAC name you can see here: catechol, benzene 1,2 diol, resorcinol, benzene 1,3 diol, and hydroquinone or quinol, benzene 1,4 diol. C. Ethers. Common names of ethers are derived from the names of alkyl or aryl groups written as separate words in alphabetical order and adding the word ether at the end. For example, CH3OC2H5, that is ethyl methyl ether. Table 11.2 Common and IUPAC names of some ethers. You can see here. If both the alkyl groups are the same, the prefix di is added before the alkyl group. For example, C2H5O, C2H5 is diethyl ether. According to IUPAC system of nomenclature, ethers are regarded as hydrocarbons, derivatives in which a hydrogen atom is replaced by an OR or OAR group, where R and AR represents alkyl and aryl groups, respectively. The larger group is chosen as the parent hydrocarbon. The names of a few ethers are given as example in table 11.2, which you have already seen. 11.3 Structures of functional groups. In alcohols, the oxygen of the OH group is attached to carbon by sigma bond formed by the overlap of a sp3 hybridized orbital of carbon with a sp3 hybridized orbital of oxygen. Figure 11.1 depicts the structural aspects of methanol, phenol and methoxy methane. You can see here methanol, phenol and methoxy methane structure. The bond angle in alcohols is slightly less than the tetrahedral angle 109 degree 28 inches. It is due to the repulsion between the unshared electron pairs of oxygen. In phenols, the OH group is attached to sp2 hybridized carbon of an aromatic ring. The carbon-oxygen bond length is 136 picometer in phenol, is slightly less than that in methanol. This is due to number 1, partial double bond character on account of the conjugation of unshared electron pair of oxygen with the aromatic ring. Number 2, sp2 hybridized state of carbon to which oxygen is attached. In ethers, the 4 electron pairs, that is the 2 bond pairs and 2 lone pairs of electrons on oxygen, are arranged approximately in a tetrahedral arrangement. The bond angle is slightly greater than the tetrahedral angle due to the repulsive interaction between the two bulky groups, that is the two bulky R groups. The CO bond length is 141 picometer, is almost the same as in alcohols. 11.4 Alcohols and phenols. 11.4.1 Preparation of alcohols. Alcohols are prepared by the following methods. Number 1, from alkenes. Number 1, by acid catalyzed hydration. Alkenes react with water in the presence of acid as catalyst to form alcohols. In case of unsymmetrical alkenes, the addition reaction takes place in accordance with Markovnikov's rule. See this mechanism. Step 1, protonation of alkene to form carbocation by electrophilic attack of H3O positive. Step 2 is nucleophilic attack of water on carbocation. And step 3 is deprotonation to form an alcohol. Hydroboration oxidation was first reported by H.C. Brown in 1959 for his studies on boron-containing organic compounds. Brown shared the 1979 Nobel Prize in Chemistry with G. Wittig. Number 2, by hydroboration oxidation. Diborane BH3 twice reacts with alkenes to give trialkyl boranes as addition product. This is oxidized to alcohol by hydrogen peroxide in the presence of aqueous sodium hydroxide. See this reaction. The addition of borane to the double bond takes place in such a manner that the boron atom gets attached to the sp2 carbon carrying greater number of hydrogen atoms. The alcohol so formed looks as if it has been formed by the addition of water to the alkene in a way opposite to Markovnikov's rule. In this reaction, alcohol is obtained in excellent yield. Number 2, from carbonyl compounds. Number 1, by reduction of aldehydes and ketones. Aldehydes and ketones are reduced to the corresponding alcohols by addition of hydrogen in the presence of catalyst, that is catalytic hydrogenation. The usual catalyst is a finely divided metal such as platinum, palladium or nickel. It is also prepared by treating aldehydes and ketones with sodium borohydride NaBH4 or lithium aluminum hydride LiAlH4. Aldehydes yield primary alcohols, whereas ketones give secondary alcohols. You can see these reaction. RCHO plus H2 in the presence of PD, that is forming RCH2OH. RCOR- in the presence of NaBH4, it is forming RCHR- and CH के साथ OH और है. The number in front of the reagents along the arrow indicated that the second reagent is added only when the reaction with first is complete. Number 2, by reduction of carboxylic acid and esters. Carboxylic acids are reduced to primary alcohols in excellent yields by lithium aluminum hydride, a strong reducing agent, that is RCOH. In the presence of LiAlH4 and H2O, it is forming RCH2OH. However, LiAlH4 is an expensive reagent and therefore used for preparing special chemicals only. Commercially, acids are reduced to alcohol by converting them to the esters, followed by their reduction using hydrogen in the presence of catalyst, that is a catalytic hydrogenation. RCOOH in the presence of ROH and H ion, it is forming RCOR-. In the presence of H2 and catalyst, it is forming RCH2OH plus R-OH. Number 3, from Grignard reagents. Alcohols are produced by the reaction of Grignard reagents with aldehydes and ketones. The first step of the reaction is the nucleophilic addition of Grignard reagent to the carbonyl group to form an adduct. Hydrolysis of the adduct yields an alcohol. You can see this reaction here. The overall reaction using different aldehydes and ketones are as follows. See all the 3 reactions. The reaction of Grignard reagent with methanol produces a primary alcohol, with other aldehydes secondary alcohols, and with ketones tertiary alcohols. You will notice that the reaction produces a primary alcohol with methanol, a secondary alcohol with other aldehydes, and tertiary alcohol with ketones. 11.4.2 Preparation of phenols. Phenol, also known as carbolic acid, was first isolated in the early 19th century from coal tar. Nowadays, phenol is commercially produced synthetically in the laboratory. Phenols are prepared from benzene derivatives by any of the following methods. Number 1, from haloarenes. Chlorobenzene is fused with NaOH at 623 Kelvin and 320 atmospheric pressure. Phenol is obtained by acidification of sodium phenoxide, so produced. See this reaction? Number 2, from benzene sulfonic acid. Benzene is sulfonated with oleum and benzene sulfonic acid, so formed is converted to sodium phenoxide on heating with molten sodium hydroxide. Acidification of the sodium salt gives phenol. See this reaction. Third, from diazonium salts. A diazonium salt is formed by treating an aromatic primary amine with nitrous acid, that is NaNO2 plus HCl at 273 to 278 Kelvin. Diazonium salts are hydrolyzed to phenols by warming with water or by treating with dilute acids. See this reaction. Most of the worldwide production of phenol is from cumene. Fourth is from cumene. Phenol is manufactured from the hydrocarbon cumene. Cumene, that is isopropyl benzene, is oxidized in the presence of air to cumene hydroperoxide. It is converted to phenol and acetone by treating it with dilute acid. Acetone, a byproduct of this reaction, is also obtained in large quantities by this method. See this reaction. 11.4.3 Physical properties. Alcohols and phenols consist of two parts, an alkyl-aryl group and a hydroxyl group. The properties of alcohols and phenols are chiefly due to the hydroxyl group. The nature of alkyl and aryl groups simply modify these properties. Boiling points. The boiling points of alcohols and phenols increase with increase in the number of carbon atoms, that is increase in van der Waals forces. In alcohols, the boiling points decrease with increase of branching in carbon chain because of decrease in van der Waals forces with decrease in surface area. The OH group in alcohols and phenols is involved in intermolecular hydrogen bonding as shown below. See this. It is interesting to note that boiling points of alcohols and phenols are higher in comparison to other classes of compounds, namely hydrocarbons, ethers, haloalkanes, and haloarenes of comparable molecular masses. For example, ethanol and propane have comparable molecular masses, but their boiling points differ widely. The boiling point of methoxymethane is intermediate of the two boiling points. See this, ethanol molecular mass and boiling point is 46 and 351 Kelvin. Methoxymethane, that is 46 and 248 Kelvin, and propane 44 to 231 Kelvin. The high boiling points of alcohols are mainly due to the presence of intermolecular hydrogen bonding in them, which is lacking in ethers and hydrocarbons. Solubility. Solubility of alcohols and phenols in water is due to their ability to form hydrogen bonds with water molecules as shown. The solubility decreases with increase in size of alkyl or aryl groups. Several of the lower molecular mass alcohols are miscible with water in all proportions. 11.4.4 Chemical reactions. Alcohols are versatile compounds. They react both as nucleophiles and electrophiles. The bond between OH is broken when alcohol reacts as nucleophiles. Here you can see alcohols as nucleophiles. The bond between CO is broken when they react as electrophiles. Protonated alcohol reacts in this manner. And now the protonated alcohol as electrophiles. Based on the cleavage of OH and CO bond, the reaction of alcohols and phenols may be divided into two groups. A. Reaction involving cleavage of OH bond. 1. Acidity of alcohols and phenols. Number 1. Reaction with metals. Alcohols and phenols react with active metals such as sodium, potassium, and aluminium to yield corresponding alkoxide, phenoxide, and hydrogen. 2ROH plus 2Na gives out 2RONA plus H2, that is the sodium alkoxide. Here you can see the next reaction. Here you can see the phenol is forming the sodium phenoxide. In addition to this, phenol react with aqueous sodium hydroxide to form sodium phenoxides. The above reactions show that alcohols and phenols are acidic in nature. In fact, alcohols and phenols are Bronsted acids, that is, they can donate a proton to a stronger base. Number 2. Acidity of alcohols. The acidic character of alcohol is due to the polar nature of OH bond. An electron releasing group increases electron density on oxygen, tending to decrease the polarity of OH bond. This decreases the acid strength. For the reason, the acid strength of alcohols decreasing in the order primary, secondary, and tertiary, you can see here. Alcohols are, however, weaker acid than water. This can be illustrated by the reaction of water with an alkoxide, base, acid, conjugate acid, and conjugate base. You can see all four. This reaction shows the water is a better proton donor than alcohol. Also in the above reaction, we note that an alkoxide ion is a better proton acceptor than hydroxide ion, which suggests that alkoxide are stronger bases. Sodium methoxide is a stronger base than sodium hydroxide. Alcohol act as Bronsted bases as well. It is due to the presence of unshared electron pairs on oxygen, which makes them proton acceptor. Number third, acidity of phenols. The reaction of phenol with metals, that is sodium and aluminium and sodium hydroxide, indicates its acidic nature. The hydroxyl group in phenol is directly attached to the sp2 hybridized carbon of benzene ring, which acts as an electron withdrawing group. Due to this, the charge distribution in phenol molecule as depicted in its resonance structure causes the oxygen of OH group to be positive. See this? The reaction of phenol with aqueous sodium hydroxide indicates that phenol are a stronger acid than alcohols and water. Let us examine how a compound in which hydroxyl group attached to an aromatic ring is more acidic than one in which hydroxyl group is attached to an alkyl group. The ionization of an alcohol and a phenol takes place as follows. Due to higher electronegativity of sp2 hybridized carbon of phenol to which OH is attached, electron density decreases on oxygen. This increases the polarity of OH bond and results in an increase in ionization of phenols than that of alcohols. Now let us examine the stabilities of alkoxide and phenoxide ions. In alkoxide ion, the negative charge is localized on oxygen, while in phenoxide ion, the charge is delocalized. The delocalization of negative charge makes phenoxide ion more stable and favors the ionization of phenol. Although there is also a charge delocalization in phenol, its resonance structure have charge separation, due to which the phenol molecule is less stable than phenoxide ion. In substituted phenol, the presence of electron withdrawing group such as nitro group enhances the acidic strength of phenol. This effect is more pronounced when such a group is present at ortho and para position. It is due to the effective delocalization of negative charge in phenoxide ion when substituent is at ortho or para position. On the other hand, electron-releasing groups such as alkyl group in general do not favor the formation of phenoxide ion, resulting in decrease in acidic strength. Cresols, for examples, are less acidic than phenol. The greater the pKa value, the weaker the acid. You can see in the table 11.3 pKa values for some phenol and ethanol. I am reading the values. Orthonitrophenol 7.2, metanitrophenol 8.3, paranitrophenol 7.1, phenol 10, orthocresol 10.2, metacresol 10.1, paracresol 10.2 and ethanol 15.9. From the above data, you will note that the phenol is a million times more acidic than ethanol. Number 2, esterification. Alcohols and phenols react with carboxylic acids and acid chlorides and acid anhydrides to form esters. See all these three reactions. The reaction with carboxylic acid and acid anhydride is carried out in the presence of a small amount of concentrated sulfuric acid. The reaction is reversible and therefore water is removed as soon as it is formed. The reaction with acid chloride is carried out in the presence of a base, pyridine, so as to neutralize HCl, which is formed during the reaction. It shifts the equilibrium to the right hand side. The introduction of acetyl CH3CO group in alcohols or phenols is known as acetylation. Acetylation of salicylic acid produces aspirin. Aspirin possesses analgesic, anti-inflammatory and antipyretic properties. See this reaction, formation of acetyl salicylic acid from salicylic acid. B. Reactions involving cleavage of carbon-oxygen bond in alcohols. The reaction involving cleavage of CO bond takes place only in alcohols. Phenol shows the type of reaction only with zinc. Number 1. Reaction with hydrogen halides. Alcohols reacts with hydrogen halides to form alkyl halide. ROH plus HX gives out RX plus H2O. The difference in reactivity of three classes of alcohols with HCl distinguishes them from one another, that is Lucas test. And alcohols are soluble in Lucas reagent, that is concentrated HCl and ZnCl2, while their halides are immiscible and produce turbidity in solution. In case of tertiary alcohols, turbidity is produced immediately as they form the halides easily. Primary alcohols do not produce turbidity at room temperature. Number 2. Reaction with phosphorus trihalides. Alcohols are converted to alkyl bromides by reaction with phosphorus tribromide. Number third, dehydration. Alcohols undergo dehydration, that is removal of molecule of water to form alkenes on treating with a protic acid. Example, concentrated H2SO4 or H3PO4, or catalysts such as anhydrous zinc chloride or alumina. See this reaction. Ethanol undergoes dehydration by heating it with concentrated H2SO4 at 443 Kelvin. See this reaction. Secondary and tertiary alcohol are dehydrated under milder conditions. For example, the both reaction you can see here. Thus, the relative case ease of dehydration of alcohols follows the following order. Tertiary is greater than secondary, is greater than primary. The mechanism of dehydration of ethanol involves the following steps. Tertiary carbocations are more stable and are therefore easier to form than secondary and primary carbocations. Tertiary alcohols are the easiest to dehydrate. Here you can see the mechanism. Step 1, formation of protonated alcohol. Step 2, formation of carbocation. It is the slowest step and hence the rate determining step of the reaction. Step 3 is the formation of ethene by elimination of proton. The acid used in step 1 is released in step 3 to derive the equilibrium to the right. Ethene is removed as it is formed. Fourth, oxidation. Oxidation of alcohol involves the formation of carbon-oxygen double bond with cleavage on often OH and CH bonds. Such a cleavage and formation of bonds occur in oxidation reaction. These are also known as dehydrogenation reaction, as these involves loss of a dihydrogen from an alcohol molecule. Depending on the oxidizing agent used, a primary alcohol is oxidized to an aldehyde, which in turn is oxidized to a carboxylic acid. See this reaction? RCH2OH, on oxidation it is forming aldehyde and carboxylic acid. Strong oxidizing agents such as acidified potassium permanganate are used for getting carboxylic acids from alcohols directly. CrO3 in hydrous medium is used as the oxidizing agent for the isolation of aldehydes. RCH2OH forming RCHO in the presence of CrO3. A better reagent for oxidation of primary alcohols to aldehydes in good yield is pyridinium chlorochromate (PCC), a complex of chromium trioxide with pyridine and HCl. Secondary alcohols are oxidized to ketones by chromic anhydride. See this reaction. Secondary alcohol is forming ketone. Tertiary alcohols do not undergo oxidation reaction. Under strong reaction conditions such as strong oxidizing agents KMNO4 and elevated temperature, cleavage of various CC bond takes place and a mixture of carboxylic acids containing lesser number of carbon atom is formed. When the vapors of a primary or a secondary alcohol are passed over heated copper at 573 Kelvin, dehydrogenation takes place and an aldehyde or a ketone is formed while tertiary alcohols undergo dehydration. Biological oxidation of methanol and ethanol in the body produces the corresponding aldehyde followed by the acid. At times, the alcoholics by mistake drink ethanol mixed with methanol, also called denatured alcohol. In the body, methanol is oxidized first to methanol and then to methanoic acid, which may cause blindness and death. A methanol poisoned patient is treated by giving intravenous infusions of diluted ethanol. The enzyme responsible for oxidation of aldehyde HCHO to acid is swammed, allowing time for kidneys to excrete methanol. C. Reactions of phenols. Following reactions are shown by phenols only. Number 1, electrophilic aromatic substitution. In phenols, the reaction that take place on aromatic ring are electrophilic substitution reaction. The OH group attached to the benzene ring activates it towards electrophilic substitution. Also, it directs the incoming group to ortho and para positions in the ring, as these positions become electron rich due to the resonance effect caused by OH group. The resonance structures are shown under acidity of phenols. Common electrophilic aromatic substitution reaction taking place in phenol are as follows. Number 1, nitration. With dilute nitric acid at low temperature 298 Kelvin, phenol yields a mixture of ortho and para nitrophenols. See this reaction. The ortho and para isomers can be separated by steam distillation. Orthonitrophenol is steamed volatile due to intramolecular hydrogen bonding, while paranitrophenol is less volatile due to intermolecular hydrogen bonding, which causes the association of molecules. With concentrated nitric acid, phenol is converted to 2,4,6 trinitrophenol. The product is commonly known as picric acid. The yield of the reaction product is poor. You can see here the structure of picric acid. Important it is. 2,4,6 trinitrophenol is a strong acid due to the presence of 3 electron withdrawing NO2 groups which facilitate the release of hydrogen ions. Nowadays, picric acid is prepared by treating phenol first with concentrated sulfuric acid, which converts it to phenol 2,4 disulfonic acid, and then with concentrated nitric acid to get 2,4,6 trinitrophenol. Can you write the equation of the reactions involved? Number 2, halogenation. On treating phenol with bromine, different reactions produced are formed under different experimental conditions. A. When the reaction is carried out in solvents of low polarity such as CHCl3 or CS2 and at low temperature monobromophenols are formed. See this. The usual halogenation of benzene takes place in the presence of a Lewis acid such as FeBr3, which polarizes the halogen molecule. In case of phenol, the polarization of bromine molecules take place even in the absence of Lewis acid. It is due to the highly activating effect of OH group attached to the benzene ring. B. When phenol is treated with bromine water, 2,4,6 tribromophenol is formed as white precipitate. Here you can see this reaction. Number 2, Kolbe's reaction. Phenoxide ion generated by treating phenol with sodium hydroxide is even more reactive than phenol towards electrophilic aromatic substitution. Hence, it undergoes electrophilic substitution with carbon dioxide, a weak electrophile. Orthohydroxy benzoic acid is formed as the main reaction product. See the formation of salicylic acid. Third, Reamer-Tiemann reaction. On treating phenol with chloroform in the presence of sodium hydroxide, a CHO group is introduced at ortho position of benzene ring. This reaction is known as Reamer-Tiemann reaction. The intermediate substituted benzyl chloride is hydrolyzed in the presence of alkali to produce salicylaldehyde. See this reaction, the intermediate product and the salicylaldehyde. Fourth, reaction of phenol with zinc dust. Phenol is converted to benzene on heating with zinc dust. Fifth, oxidation. Oxidation of phenol with chromic acid produces a conjugated diketone known as benzequinone. In the presence of air, phenols are slowly oxidized to dark colored mixtures containing quinones. See here benzoquinone formation. 11.57 Some commercially important alcohols. Methanol and ethanol are among the two commercially important alcohols. First, methanol. Methanol, CH3OH, also known as wood spirit, was produced by destructive distillation of wood. Today, most of the methanol is produced by catalytic hydrogenation of carbon monoxide at high pressure and temperature and in the presence of ZNO Cr2O3 catalyst. CO plus 2H2O in the presence of ZNO Cr2O3 at 573 to 673 Kelvin and the pressure is 200 to 300 atmospheric pressure, it is forming CH3OH, that is methanol. Methanol is a colorless liquid and boils at 337 Kelvin. It is highly poisonous in nature. Ingestion of even small quantities of methanol can cause blindness and large quantities causes even death. Methanol is used as a solvent in paints, varnishes and chiefly for making formaldehyde. Ethanol, C2H5OH, is obtained commercially by fermentation. The oldest method is from sugars. The sugar in molasses, sugarcane, or fruits such as grapes is converted to glucose and fructose, both of which have the formula C6H12O6 in the presence of an enzyme, invertase. Glucose and fructose undergo fermentation in the presence of another enzyme, zymase, which is found in yeast. C12H22O11 plus H2O. In the presence of invertase, it is forming glucose and fructose. And C6H12O6, in the presence of zymase, it is forming 2C2H5OH plus 2CO2. In winemaking, grapes are the source of sugars and yeast. As grapes ripen, the quantity of sugar increases and yeast grows on the outer skin. When grapes are crushed, the sugar and the enzyme come in contact and fermentation starts. Fermentation takes place in anaerobic condition, that is in absence of air. Carbon dioxide is released during fermentation. The action of zymase is inhibited once the percentage of alcohol formed exceeds 14%. If air gets into fermentation mixture, the oxygen of air oxidizes ethanol to ethanoic acid, which in turn destroys the taste of alcoholic drinks. Ethanol is a colorless liquid with boiling point 351 Kelvin. It is used as a solvent in paint industry and in the preparation of a number of carbon compounds. The commercial alcohol is made unfit for drinking by mixing in it some copper sulfate to give it a color, and pyridine, a foul smelling liquid. It is known as denaturation of alcohol. Nowadays, large quantities of ethanol are obtained by hydration of ethene. Ingestion of ethanol acts on the central nervous system in moderate amounts. It affects judgment and lowers inhibition. Higher concentration causes nausea and loss of consciousness. Even at higher concentration, it interferes with spontaneous respiration and can be fatal. 11.6 Ethers. Preparation of ethers. Number 1, by dehydration of alcohols. Alcohols undergo dehydration in the presence of protic acids, that is H2SO4, S3PO4. The formation of reaction product alkene or ether depends on the reaction conditions. For example, ethanol is dehydrated to ethene in the presence of sulfuric acid at 443 Kelvin. At 413 Kelvin, methoxy ethane is the main product. See here the reaction. Diethyl ether has been used widely as an inhalation anesthetic, but due to its slow effect and an unpleasant recovery period, it has been replaced as an anesthetic by other compounds. The formation of ether is a nucleophilic bimolecular reaction, SN2, involving the attack of alcohol molecule on a protonated alcohol as indicated below. First reaction, second reaction. Acidic dehydration of alcohols to give an alkene is also associated with substitution reaction to give an ether. The method is suitable for the preparation of ethers having primary alkyl groups only. The alkyl group should be unhindered and the temperature be kept low. Otherwise, the reaction favors the formation of alkene. The reaction follows SN1 pathway when the alcohol is secondary or tertiary, about which you will learn in higher classes. However, the dehydration of secondary and tertiary alcohols to give corresponding ethers is unsuccessful as elimination competes over substitution, and as a consequence, alkenes are easily formed. Can you explain why is bimolecular dehydration not appropriate for the preparation of methyl ether? Number 2, Williamson synthesis. It is an important laboratory method for the preparation of symmetrical and unsymmetrical ethers. In this method, an alkyl halide is allowed to react with sodium alkoxide. Ethers containing substituted alkyl group secondary or tertiary may also be prepared by this method. The reaction involves SN2 attack of an alkoxide ion on primary alkyl halide. Alexander William Williamson, 1924 to 1904, was born in London of Scottish parent in 1849. He became professor of chemistry at University College, London. See this reaction mechanism. Better results are obtained if the alkyl halide is primary. In case of secondary and tertiary halides, elimination of competes over substitution. If a tertiary alkyl halide is used, an alkene is the only reaction product and no ether is formed. For example, the reaction of CH3ONA with CH3 whole thrice CBr gives exclusively 2-methylpropene. See this reaction. It is because alkoxide are not only nucleophiles but strong bases as well. They react with alkyl halides leading to elimination reactions. Phenols are also converted to ethers by this method. In this, phenol is used as the phenoxide moiety. See this. 11.6.2 Physical properties. The CO bonds in ether are polar and thus ethers have a net dipole moment. The weak polarity of ethers do not appreciably affect their boiling points, which are comparable to those of alkanes of comparable molecular masses but are much lower than the boiling points of alcohols as shown in the following cases. See here N-pentane 3091.1, ethoxy ethane that is 307.6 Kelvin and butane 1-ol that is 390 Kelvin. The large difference in boiling points of alcohols and ethers is due to the presence of hydrogen bonding in alcohols. The miscibility of ethers with water resembles those of alcohols of the same molecular mass. Both ethoxy ethane and butane 1-ol are miscible to almost the same extent, that is 7.5 and 9 gram per 100 ml water respectively, while pentane is essentially immiscible with water. Can you explain this observation? This is due to the fact that just like alcohols, oxygen of ether can also form hydrogen bonds with water molecule as shown. 11.6.3 Chemical reaction. Number 1, cleavage of CO bonds in ethers. Ethers are the least reactive of the functional group. The cleavage of CO bonds in ethers take place under drastic condition with excess of hydrogen halides. The reaction of dialkyl ethers gives 2 alkyl halides molecules. Both reactions are here. Alkyl aryl ethers are cleaved at the alkyl oxygen bond due to the more stable aryl oxygen bond. The reaction yields phenol and alkyl halide. Ethers with 2 different alkyl groups are also cleaved in the same manner. ROR dash plus HX gives out RX plus R dash OH. The order of reactivity of hydrogen halide is as follows. HI is greater than HBr is greater than HCl. The cleavage of ethers takes place with concentrated HI or HBr at high temperature. Here you can see the mechanism. The reaction of an ether with concentrated HI starts with protonation of ether molecule. Step 2. Iodide is a good nucleophile. It attacks the least substituted carbon of the oxonium ion formed in step 1 and displaces an alcohol molecule by SN2 mechanism. Thus, in the cleavage of mixed ether with two different alkyl groups, the alcohol and alkyl iodide formed depend on the nature of alkyl groups. When primary or secondary alkyl groups are present, it is the lower alkyl group that forms alkyl iodide SN2 reaction. When HI is in excess and the reaction is carried out at high temperature, ethanol reacts with another molecule of HI and is converted to ethyl iodide. However, when one of the alkyl group is a tertiary group, the halide formed is a tertiary halide. It is because in step 2 of the reaction, the departure of leaving group HOCH3 creates a more stable carbocation and the reaction follows SN1 mechanism. In case of anisole methyl phenyloxonium ion, this is formed by protonation of ether. The bond between OCH3 is weaker than the bond between OCH6H5 because a carbon of phenyl group is sp2 hybridized and there is a partial double bond character. See both this reaction, one is slow and one is fast. Therefore, the attack by I negative ion breaks OCH3 bond to form CH3HI and phenols do not react further to give halides because the sp2 hybridized carbon of phenol cannot undergo nucleophilic substitution reaction needed for conversion to the halide. Number 2, electrophilic substitution. The alkoxy group is ortho-para directing and activates the aromatic ring towards electrophilic substitution in the same way as in phenol. Number 1, halogenation. Phenyl alkyl ethers undergo usual halogenation in the benzene ring. Example, anisole undergo bromination with bromine in ethanoic acid even in the absence of iron bromide catalyst. It is due to the activation of benzene ring by the methoxy group. Para isomer is obtained in 90% yield. Here you can see anisole is forming para bromo anisole and ortho bromo anisole. Para-bromo is the major one and the ortho-bromoanisole is the minor one, and this reaction happens in the presence of ethanoic acid and Br2. Number 2, Friedel-Crafts reaction. Anisole undergoes Friedel-Crafts reaction, that is the alkyl and acyl groups are introduced at ortho and para position by reaction with alkyl halide and acyl halide in the presence of anhydrous aluminum chloride, a Lewis acid as catalyst. See this reaction. See the major product and the minor product. Next reaction. Third is the nitration. Anisole reacts with a mixture of concentrated sulfuric acid and nitric acid to yield a mixture of ortho and para nitroanisole. See this reaction. The 2 nitroanisole, minor one it is. 4 nitroanisole, major one it is. Summary. Alcohols and phenols are classified, number 1, on the basis of the number of hydroxyl groups and second, according to the hybridization of the carbon atom sp3 or sp2 to which the OH group is attached. Ethers are classified on the basis of groups attached to the oxygen atom. Alcohols may be prepared by hydration of alkenes in presence of an acid, by hydroboration oxidation reaction from carbonyl compounds, and number 1, catalytic reduction, and number 2 is the action of Grignard reagents. Phenols may be prepared by substitution of halogen atom in haloarenes and sulfonic acid group in aryl sulfonic acids by OH group, by hydrolysis of diazonium salts and industrially from cumene. Alcohols are higher boiling than the other classes of compounds, namely hydrocarbons, ethers and haloalkanes of comparable molecular masses. The ability of alcohols, phenols and ethers to form intermolecular hydrogen bonding with water makes them soluble in it. Alcohols and phenols are acidic in nature. Electron withdrawing groups in phenol increases its acidic strength and electron releasing groups decrease it. Alcohols undergo nucleophilic substitution with hydrogen halides to yield alkyl halides. Dehydration of alcohols gives alkenes. On oxidation, primary alcohols yield aldehydes with mild oxidizing agents and carboxylic acids with a strong oxidizing agent, while secondary alcohols yield ketones. Tertiary alcohols are resistant to oxidation. The presence of OH groups in phenols activates the aromatic rings towards electrophilic substitution and directs the incoming group to ortho and para position due to resonance effect. Riemann-Tiemann reaction of phenol yields salicylaldehyde. In presence of sodium hydroxide, phenol generates phenoxide ion, which is even more reactive than phenol. Thus, in alkaline medium, phenol undergoes cold-base reaction. Ethers may be prepared by number 1, dehydration of alcohols, number 2, Williamson synthesis. The boiling points of ether resemble those of alkanes while their solubility is comparable to those of alcohols having same molecular mass. The CO bond in ethers can be cleaved by hydrogen halides. In electrophilic substitution, the alkoxy group activates the aromatic ring and directs the incoming group to ortho and para positions. Chapter done. फाइनली सारी ऑडियो बुक बन गई है क्लास 11th एंड 12th की केमिस्ट्री। आई एम वेरी हैप्पी। अब आप लोग अपना रिवीजन अच्छे से कर सकते हैं। बहुत जल्दी इनकी कंपाइल्ड फॉर्म भी आप लोगों के साथ में अवेलेबल होगी। बच्चों, इनको अपने दोस्तों के साथ में ज़्यादा से ज़्यादा शेयर करिए ताकि उनकी भी हेल्प हो सके, क्योंकि अभी बहुत सारे बच्चों को पता ही नहीं है कि इस तरह की ऑडियो बुक्स भी अवेलेबल हैं जो आपके रिवीजन में इतनी ज़्यादा हेल्प करती हैं। और अगर आपको मेरा वीडियो पसंद आया हो तो इसे लाइक कीजिएगा, चैनल पे नए हो तो सब्सक्राइब कीजिएगा। मिलते हैं नए वीडियो में next time. Till then, just stay tuned with me. All the best for your exam. Bye bye. Take care, everyone.